Hi. So let's try to solve a problem with regards to bracketing methods, and then the problem is already in your screen right now. I will read it. Given this function f of x is equal to negative 12 minus 21x plus 18x squared minus 2.75x cubed, determine the first root of the function with bisection, and the other one will be false position. And then for these two methods, we will use initial guesses of x equal to negative 1 and x equal to 0, and a stopping criterion of 1%. So, alright, our function is, okay, this is the first problem. So our function is equal to negative 12 minus 21x plus 18x squared, then minus 2.75x cubed. Okay, and then we're going to use the XL and XU. This is negative 1 and this is 0. Okay, that is the lower boundary, and the stepping criterion, yes, it's just 1%. Okay, now from here, when we use the bracketing method, remember we can probably test first if there is a root. We will do that. So if you test here, test if there is a root, test if there is at least one root. We will do like f of xl times f of xu should be less than 0. Okay, it should be negative. Our f of xl is f of negative 1. We will compute that one here using my calculator. Okay, I have a calculator. It will just, I can write the function in the calculator, this one, and then I will input the independent variable x, and then I can solve for the function f of x. So minus 12 minus 21x plus 18x squared minus 2.75 cubed. Okay, then I will put here negative 1. 29.75. So this is 29.75, and then of course our f of 0 from here, it's quite obvious. Everything is 0 except for negative 12. And then since this is less than 0, this the product is less than 0, then of course we will say that there is at least one root. Now to proceed, let's go to the first iteration. Okay, first iteration. Like that. Our root is at the middle. That is our assumption, it's our guess. XR1 is equal to XL plus XU over 2. Okay, so this is XL or XL1 plus XU1 over 2, and of course this is equal to negative 1 plus 0 over 2, which will give us negative 0.5. Okay, negative 0.5. That is our first estimate of the root. Okay, that is negative 0.5. Now, before going to the second iteration, well, at this moment we cannot compute the error because this is our first root estimate. We do not know this is the first estimate, so until we will compute the second iteration, the second root estimate, then we can compute the error. So after here, we will test first before we will move to the second iteration. So anyway, no problem. Let's move to second iteration. But then before we use the boundaries, we need to test first. If you remember, test, and the test is, I think, is f of xl times of f of xr. Is this less than, greater than 0, or even equal to 0? Okay, so this is less than, greater than, or equal to 0. If less than 0, we know what to do. We will set the new upper boundary, new, is equal to the root. Okay, if it is greater than 0, then we will set x lower new is equal to the root, and if it is equal to 0, fortunately, xr is the root. It is the root. Okay, because it's equal to 0. Now, let's try to test this one first. We can, or we'll just do it here. F of, what is this? This is the test. F of XL in this case is f of -1. Okay, let me just write this one. Is this is a test? So is this less than, greater than, or equal to 0? That's the question. So f of XL, f of -1 times f of -0.5. Okay, so I will use my calculator to compute for 0.5. So f of -0.5 is 3.3437. So this one is -1. This is 29.75 times 3.3437. So this is greater than 0. No need to know the value there. Therefore, we will set greater than 0. Set XL2 is equal to XR1. So XR1 now is really -0.5. XR1 or -0.5, something like that. Okay, and then we will proceed. So we'll compute XR2 is equal to XL2 plus XU2 over 2. Our upper boundary is still the same, it's 0 because it didn't change, only the lower boundary. So after here, this is equal to what? Lower boundary is here. So -0.5 plus the upper boundary is 0, okay, over 2. Okay, this is XR2. Okay, that our estimate is -0.25. Okay, -0.25. Why? Because from here, when we change the lower boundary to the root, which is -0.5, we are now using 0 and -0.5. So from there, we will try to estimate the root. Okay, so we abandon now the -1. Okay, from here, this is the new root estimate, and of course we can compute for the error if you want. Error is of course the absolute value of, remember, the current value minus the previous value over the current value, and then times 100 to make it percentage. We have here current value -0.25 minus -0.5 over -0.25 times 100. What's the error there? Let's do that. -0.25 plus 0.5 divide -0.25 times 100. Oh, that is 100%. Of course, because yeah. Anyway, this is 100%. Very big error. Okay, so not good. And of course, this is greater than the stopping criterion, which is 1%. So you proceed. We will proceed to the third iteration. Okay. So we will not stop because the the error is still greater than the stopping criterion, something like that. Now you proceed to the third iteration. Okay, third iteration. Okay. So in the third iteration, you have to test first. So test f of XL times f of XR. Okay, so what is this? We will just test that one. F of XL is f of the lower here boundary before is -0.5 times f of XR, which is -0.25. Okay, so f of -0.5, I think we can pick that one. Where is that? Here. 3.3437 times f of -0.25, we will do that. Squared, negative, we may write this first, -12 minus 21x plus 18 squared minus 2.75 cube. Okay, so let's try -0.25. So -0.25 is, in my computation, this is negative 5.582. Okay, so as you can see, this is less than 0. And then our test now will be, we will set, I mean not test, we will set XR. Okay, we will make the XR the new upper boundary. Unlike here, this is greater than 0, so set XU3 is equal to XR2. Okay, which is equal to negative 0.25. So we change the boundary now from here, and then we can write here for the third iteration, we compute XR3, XL3 plus XU3 over 2. So that's what XL3, our lower boundary before was negative 0.5 plus negative 0.25, okay, over 2. Okay, how much is that? Negative 0.75 over 2, that's around negative 0.375. Okay, yeah, that's negative 0.375. That is our new estimate of the root. Okay, and then from here, the same procedure, you compute the error estimate. Let's do that. Error estimate is equal to negative 0.375 minus negative 0.25 over negative 0.375, then times 100%. And then let's see, what's the value of the error here? Negative 0.375 plus 0.25 divide negative 0.375 times 100. The error is still 33.33%, still greater than the certain criterion. And then after that, you go to the fourth iteration, and then you test, and then you will see. So this is how the this is the solution in bisection. For the we will finish this using MATLAB because maybe I'm not so sure. Maybe it will end by 6 or 7 iterations. Well, I do not know. We will use MATLAB to continue this process, but well, this is it. This is the solution, and just continue this one. Depending on the test, then we will change the boundary. Okay. Okay, so I open my MATLAB, and then I will show you how to continue the problem here in MATLAB. So if you remember, the function is f of x equal to negative 12 and so on. But the first thing that we will do is let's see the program first. And this is the current folder. I will click this one. This program, by the way, is already been it's a free source, a program. It's already incorporated in this textbook. So if you use this program, this is this is just free, but you have to modify this one if you want to make it based on your own problem. Now, this program, let's talk about the program. The program is named Bisect. That's why, of course, as you can see here, the name is bisect.m. And then the name of the function should be bisect, of course. And there's an input which is func, which is the function xl, the lower limit, xu, the upper limit, es, the stopping criterion, max it, it's like the maximum iteration. If in complicated problems, if the error is cannot be met, I mean, if the error cannot be less than the stopping criterion, then another way to stop the program is the maximum iteration, because there are times that it will not converge. So if you input maximum iteration up to 50, even if the error is not less than a stopping criterion, you can also stop the while loop, which is an infinite loop, by this max it condition. And then that's the varargen, or variable input argument. It will gather other input in the whatever. So if your functions need all these inputs, whatever it is, it will just gather that input, okay? Based depending on the sequence of the inputs. Anyway, let's make a function, an anonymous function. Let's call it f. F is equal to at x, like that. If you remember how to make an anonymous function, and then the f of x, the equation is negative 12 minus 21 times x. Okay, that's the problem, plus 18 times x squared minus 2.75 times
x cubed. Okay, so when you hit enter, f is already been added in the workspace. Now let's make it a little bit bigger. I will not talk about more about the I mean about a program. I will just want to solve this one for now. We will talk about that in the future lectures. For the meantime, this is f, and then if you want to input something there, we can do it. No problem. Okay, so f here is already defined. It's in the workspace, and then we are now ready to use the program. So, well, the program is simply we can. I mean, it's already saved, no problem. And then we can just call it. Let's say. Remember, by the way, I forgot. Here you have seen this one function, and then root. There is this bracket root ea, and then iter. This program will output three arguments. First is the root. Next is the error, and then the last one will be the iter. So if you will run this now, we can call this program like this. Let's in three ways. Root. You can copy that one. It doesn't matter. Iter, and then is equal to bisect. Your func is f. Okay, this is your f. xl is the lower limit, and this is -1. The upper limit is 0, and then es summing iteration is 1%. Maximum iteration, let's just make it well, for now let's make it 50, and then that's all. No need for that input variable arguments, because no other input here. When we click this one, we will see the result. Hit enter. Okay, you see. Let's make it bigger a little bit, like that. Root is equal to -0.4180, and then the error is already been 0.9346%, and the iteration is 8. This is in MATLAB and bisection. Now, if you want this program to display the roots as it moves, I mean as it solves the problem, because here we do not know whether our computation a while ago was correct in the blackboard, so we will see that one. But anyway, it took us 8 iteration for bisection, and then the error is 0.9346, and then it stops. Remember, our maximum iteration is 50, so iteration is only 80 here. We can put here, we can modify the program a little bit. We can just look at the program here. Inside the while loop, we can put here display XR. We can do that. We can use put a semicolon here, and then we write display the current root is like that. Let's just do like that. The current root, or fprintf, that is possible. Maybe it's better for fprintf because it would be good. Fprintf, the current root is like that, xr. Okay, so it will print the value of xr as it moves, okay, as it runs. Okay, so let's see if it will work. Let's do it again. Let's hit up arrow here, and then hit enter. Oh, there's a problem. What's the problem here? Let me see. X equal to xr. The current root is xr. Give me the problem here. Let me check for a while. Ah, yeah. Sorry. Okay, it should have been like this. So the current root is, let's put a space a little bit, like it is xr and then /n. That would be better. /n, and then I forgot, I will put here %f. Okay, %f and then /n. Okay, that's correct. I made a mistake. And then let's run it again, up arrow here, and then enter. Okay, here. Let's see what will happen here. As it runs, okay, let's look at this one. As the program runs, let's do like this. When we hit enter, the current root is -0.5, the current root is 0.25, current is -0.375. If you remember, I think we are correct, because this is what we do in the blackboard. Then in the fourth iteration, 0.4275, -0.4062, until Current truth is negative 0.414063, and then when it compute the error, it's less than 1%, and then that's it. So the final answer here is this one, negative 0.414063. I mean, lastly here, sorry, this is the seventh iteration, I think so, and then this is the last iteration, negative 0.4180. Okay. So yeah, with that, thank you.